Our next speaker is Rubin from Sagivtech. Rubin is Sagivtech's head of development and has a broad background in HPC and GPU programming, mainly on CUDA. Is one of the first adapters of CUDA worldwide as an expert in GPU code optimizations for single and multi-GPU systems. Leads Sagivtech's GPU R&D activities, including the design and creation of a highly efficient GPU streaming infrastructure. Prior to joining Sagivtech, was team leader in Optitex, where he has built a complete 3D physical simulation pipeline running on the GPU using CUDA. You want to use your computer? Or?
I prefer, yeah.
Okay.
Okay, thank you for introducing me. So today I'm going to talk a bit about our multi-GPU infrastructure, more accurately our streaming GPU infrastructure for real-time applications. So, thank you. So first, a bit about us. Sagivtech is a software company. We're based in Israel. We've been around for the past 4-something years. We have two core domains of expertise. First is accelerating computations on massively parallel hardware, such as GPUs. The second is computer vision and image processing algorithms. We have a few license-based solutions, some libraries, infrastructure for GPU computing, which I'm going to talk about today. We have some image processing and machine learning libraries. We have H.264 decoding solution. We also do training. Later on this week, a colleague of mine from Sagivtech will give a few sessions on CUDA. And we do a lot of outsourcing projects for different software companies. We are also a local ISP partner of NVIDIA in Israel. So this slide is becoming a bit redundant. Most people already know what GPUs are and GPU computing, but I'll go through it quickly. GPUs are graphic processing units originally designed for computer graphics, games, if you will. But because the demand for graphics increased exponentially over the years, it quickly became a situation where the GPUs were actually stronger. They had more compute power than the CPU on the system. People realized that there's a potential there and started programming these GPUs to do non-graphical computations, but it was in a roundabout way, using graphical languages for things that they weren't intended. And then at some point, the hardware manufacturers realized that they have another potential market, and then they exposed the computational capabilities of these devices with APIs such as CUDA and Brook Plus, OpenCL. And today, it's relatively easy to program for your GPU. Almost every computer has a GPU, and you can download an SDK, use your favorite IDE, and start developing for it. So, as I've said, has been said, I've been programming for GPUs for quite a long time, and if in the beginning our focus was on efficiently porting code or writing code specifically designed for GPU architectures, for the massively parallel architecture where you have thousands of cores, today a significant amount of our attention shifts to actually the system. The talk that was just given before me was a good introduction, because even if you have a very strong processor, if it spends half of the time waiting for a job for the data that it needs to process to come in, then you're getting a very low efficiency from the system. So what you want to do in these systems where you have a very expensive GPU processor, you want to make sure that it's computing all the time. So that will be the main focus of this talk. Another thing that we'll touch upon is mobile GPU computing. This is the real mobile revolution, at least from my perspective. I'll talk about it a bit further on, but the next generation of mobile devices will have GPUs in them that are compute capable. So another set of projects that we are doing that I haven't talked about are European Union projects. We are part of a few of them. These are collaborative projects sponsored by the European Union, which usually involve a few companies and universities. And the idea there is to collaborate between the industry and the academia and share knowledge. One of these projects is called CNET. We are the coordinator of this project. And the idea there, in a nutshell, is you have an event. People are videoing the event. Where we want to take those videos, upload them to a server, create a high-resolution video, 3D video of that event, and then give output from that video to different clients. So here are the partners of this specific project. There is us, Sagivtech from Israel, EPFL from Switzerland, UniHB from Germany, Skills from Germany, ERS from Germany. So just to make it clear, for example, a rock concert, in such events you have hundreds to thousands of people videoing the event. Usually these videos don't really get watched or anything, sometimes uploaded to YouTube. You can see in YouTube very few people watch them, but we want to use all this information and essentially determine which videos are the interesting videos, upload them to a server, which then syncs all the videos together, does a 3D reconstruction, and creates a 3D high-resolution video of the event, and then produces output videos for different clients on social networks and so forth. This is a very ambitious project. Nobody actually expects us to succeed. But that's part of the idea. It's a FET. It's called a FET project. It's a Future Emerging Technologies project. And the idea is to aim for the stars. But we'll see how well we do. So you can imagine that there is a lot of computation that's going on that is needed for this kind of project. And it starts from the mobile device itself. We want to do as much processing or pre-processing on the device itself, enhancing the video, and also collecting data from the video, uploading it to the server so that the server can determine from the thousands of video feeds that are available, which are the ones that it really needs, because it will probably not need all those videos. And then on the server, since we intend this service to be a real-time service, then I'm saying a server, but this might end up being a cluster. All those videos need to be synced together, both in time and in space. And then 3D reconstruction needs to be done, which is a very heavy process. Today, this kind of processing takes minutes for a single frame. And then produce the output videos for the different clients. So we need to be very efficient. So this is the computational model. You have the small processors on the mobile devices, uploading the video to the central cluster. And this is what I talked about, the mobile revolution. think the most pronounced platform that is coming out is the NVIDIA K1. The exciting thing about this is that it fully supports CUDA, meaning that you have the whole ecosystem of CUDA that's been around for over 7 years. And you can use all the tools, all the libraries that you have for CUDA directly on the mobile platform. But the rest of the companies aren't asleep either. And whether it's Qualcomm or ARM or Imagination, they all have their compute GPU platforms out or coming out very shortly. And this is a very exciting time for us in that sense. We can really start doing computations, heavy computations on the mobile platforms. So how do we achieve this maximum utilization of the hardware? Well, our key point is streaming, efficient streaming. These are all applications where there's not just one task, but a stream of tasks coming in. And we want to keep the GPU working on the task continuously. So on the mobile GPU, we have to maintain high throughput. These are real-time devices. This is not a device that you want to press a button and then wait for 5 minutes or even 5 seconds. It has to happen pretty much instantaneously. And we have to do efficient streaming with many components. A mobile device has a camera, has a lot of sensors. It has to incorporate all this data, process it very efficiently, and stream the results out to the user. And a simple situation where you have a single GPU, again, you want efficient streaming to make sure that you're using the GPU for computation 100% of the time. And in a multi-GPU situation, you have all the single GPU elements plus another type of situation that we ran into a few times where you have a real-time, low-latency system, and the tasks are too big to be processed by a single GPU. A single GPU can process them, but it will take too much time, and there will be too much latency. Even if you add multiple GPUs and each one does a task, it will create too much latency. So you need to take a single task and split it up into subtasks. And then each GPU will need to do a subtask, and then all the results are aggregated back into a single result and then presented to the user. Okay, so as you can imagine, the naive approach of taking an input, pre-processing it on the CPU, copying it to the GPU, processing on the GPU, copying it back to the CPU or sending it out to the screen is not very efficient because we're not using all the elements in the system in parallel. So we encountered this problem in a number of projects and worked very hard to figure out all the little quirks and little things that are needed. And we've developed a whole methodology of how to create these applications. We have also created an infrastructure to help us achieve this high utilization. And this is the secret sauce, if you will. First, we use pipelining. It's nothing really new. Imagine if you have a single pipe and all the jobs need to pass through that pipe, then if we have different components in the system, they cannot work in parallel. But if we have a few pipes, then we can have a frame or a job passing through different elements, one job is being pre-processed by the CPU, while another job that has already been processed by the CPU the data is being copied over to the GPU. On the third pipe, the data from another job is already being processed on the GPU, and on the fourth pipe, it's being copied out or whatever. The second element is working asynchronously, and the third is using peer-to-peer communication between GPUs. So pipelining is what I explained. When you want to work with pipelining on GPUs, you need to use CUDA streams and events or OpenCL equivalent. You also need to make sure that the commands are launched in the right order so that they don't create blocks for other commands that can run before the command that you just launched. Working asynchronously. In CUDA, some commands are asynchronous, like kernel launches, but some of the default commands are synchronous, like memcopies. Usually when you launch a memcopy, the CPU, the host, will wait for the GPU to finish that request. If we want to have an efficient streaming system, everything must be asynchronous. And we do that using CUDA streams and CUDA events. We use the CUDA streams to launch the task asynchronously on different pipes, and the events to make sure that they do happen in the right order, because we do need to make sure that the data has been copied before we start working on it. Peer-to-peer communication. Peer-to-peer communication is being able to copy data directly from one GPU to another GPU, not over the network, but over the PCI Express bus. This can be very efficient. As has been mentioned here before, there are boxes today which have a few PCI Express bridge chips, and you can communicate between each pair of GPUs directly, achieving throughput of tens of gigabytes per second. The only tricky bit here is that you need to have the correct hardware set up. For example, one of the limitations is that NVIDIA has today is that all the GPUs have to use exactly the same chip. When you have the right setup, it's pretty much easy. It's pretty easy to use. All you need to do is open up the peer-to-peer communication using the CUDA API, and then all your mem copies are automatically done using this pipe. So, as I said before, we have an infrastructure for this type of technology, and we also created a demo to demonstrate this technology, since most of our projects are under NDA when we cannot talk about them. So the idea in this system is to create a multi-GPU system and achieve 100% utilization across multiple GPUs. Using this system, you can see that the green line is the utilization of the system using our infrastructure, which remains close to 100%. That's pretty much can be done. The red line is the utilization without this infrastructure, writing it in a naive way. And you can see that it drops down significantly, and when you're in 4 GPUs, you're already at 40% utilization. Okay, this is just to explain, this is a screen capture of a tool from NVIDIA called the Visual Profiler. It's a very handy tool to assess what your system is doing. All the blue blocks are computations. The brown ones are not on top. That's the CPU, but the small brown ones are actually mem copies. And the gaps are when the CPU is doing something, and the GPU is just waiting. So our demo system, which I couldn't bring today, sadly, has 5 GPUs inside, has 2 K10 boards, which each have 2 GPUs, and a GTX 660 that is used for rendering. The algorithm that we use in this demo is called total variation. It's an iterative, compute-intensive image processing algorithm. It does noise reduction and image in painting. And okay, so we are calling this a naive use case, but from what I've seen around, most applications do run this way. I mean, also the previous speaker was also talking about the new revelation when they're trying to parallelize data copy and computation. So this is your typical scenario. You have a single GPU running on a single stream, a single pipe. A frame gets captured from in this system we have a full HD 30 FPS camera. The image gets captured by the CPU, then it's copied to the GPU, processed on the GPU and displayed on the screen. We achieve 70% utilization. The utilization output is from a library from NVIDIA. And we get about 4.25 FPS. And you can see in the screen capture of the visual profiler the gaps between the blue blocks, which are the times that the GPU is not working. And we want to eliminate these. Next, we increase the pipe size of the system from 1 to 4. You can see that now there are these steps. These are the different pipes. And you can see that the processing is continuous. Our utilization has gone up to 100%. And we already achieved a 27% performance increase on a single GPU. Now, as I showed you before, this becomes much more critical the more devices that you add, because the more devices that you have more compute power. Your processing time decreases and your overhead increases. So efficient utilization of the system becomes critical to the point where you're adding more processors and you're slowing up the system. So using the 4 pipes, we are still at 100% utilization of the 4 GPUs. We are at 20 FPS, and we have near linear scaling of 3.8 compared to the single GPU using the pipelining. There are no holes in the profiling. And this is the mandatory. This research has been sponsored by the European Union. And that's it. Yeah.
What about mobile GPU?
Yeah.
Mobile GPU. In the mobile environment, the architecture of GPU, not from one vendor. The mobile environment becomes its own GPU. Quite a problem, isn't it?
Well, on the desktop or server, you also have different vendors of the GPU. It is a problem. There is an open standard today called OpenCL, which is supposed to address this problem. Sorry? The problem is that it's an open standard, and each hardware vendor implements it very differently, and the architectures are quite different. So usually you can take basic code in OpenCL and compile it for different platforms, but the minute you start to optimize it specifically for a platform, your code will not migrate from platform to platform. But that's the world we live in. It's on the desktop as well, and I don't know.